Now let's have a look at the problem. Show that we have to show that the sample mean x bar is the consistent estimator of the population mean. So what is that we have with us? We have something about sample mean is said over here. What is that we have to show? We have to show that the sample mean is a consistent estimator of population mean. So just have a look. Is it so as limit n tends to infinity? Why is it I'm taking limit n tends to infinity? Because one of the conditions for consistency is that when n tends to infinity, or when n is large, the probability that the absolute value of your statistic minus the population parameter, okay, less than a very small value epsilon, should be equal to 1, or it should tend to 1, right? This is something that we have studied. Now instead of tn, in this case it is limit n tends to infinity, probability of modulus x bar minus mu less than epsilon is equal to 1. So this is what we have to prove. Okay, now keeping this aside, what I'm going to do right now is I'm going to start with our x bar. So we already have a condition that n is infinity, so x bar follows a normal distribution, I assume. So normal mu sigma by root n. This is something we have studied earlier, and let this be equation A. Now I'm going to substitute some values in equation A. So that is what I have done over here. Limit n tends to infinity, probability of modulus x bar minus mu less than epsilon is equal to 1. What about this? Here what I'm going to do is I'm going to divide this and this term by sigma by root n. So limit n tends to infinity, probability of modulus x bar minus mu divided by sigma by root n less than epsilon divided by sigma by root n is equal to 1. Okay, now what I'm going to do is, what is this? X bar minus mu by sigma by root n is again a form of standardizing the normal distribution. So here this follows n01. I'm equating this as z, so z follows what? Again n01. So instead of writing the whole thing like this, I'm going to write it as n tends to infinity, probability of z modulus z less than epsilon divided by sigma by root n. Okay, now I have to check whether it will become 1 or not. Okay, so let me see. Now since I have written over here that probability of modulus z is less than epsilon by sigma by root n, this is a modulus sign, so how can I rewrite this as? Okay, so before that what I have to do is, now we have to check this this equation, this particular equations, let me say this as b. So check where we have to check b is equal to 1. Okay, so let's see. I'm going to write it over here once again. Limit n tends to infinity, probability of modulus z less than epsilon by sigma by root n. Okay, now what about this? Limit n tends to infinity, probability of, now since this is a modulus sign, how can I write that? Epsilon root n minus epsilon root n divided by sigma less than z less than epsilon root n by sigma. Is that fine? Okay. Now what about this? Limit n tends to infinity. How can I change this probability sign into the integration sign? How will that happen? Minus epsilon root n by sigma towards epsilon root n by sigma. Then it is f of z dz. F of z dz. What is f of z dz? Limit n tends to infinity, integral minus epsilon root n by sigma to plus epsilon by root n by epsilon into root n by sigma. What is f of z over here? I hope you remember I have written over here z follows a normal, standard normal distribution. So I will just write it over here. Z follows a standard normal distribution. So how can I write this as 1 by root 2 pi e raised to minus 1 by 2 z square dz. Right. Now this is equal to, as limit n tends to infinity, you have an n over here, you have an n over here. So as limit n tends to infinity, both these upper and lower limit becomes minus infinity and plus infinity, since root n is involved with this term, both the terms. And you have 1 by root 2 pi e raised to minus 1 by 2 z square dz, which is again what? The probability density function. This is the probability density function. And if we integrate it from minus infinity to plus infinity, what will you get? 1. So this is something you have learned earlier, and therefore this implies that what? So where have we come from? We just started from this thing, and we have proved that probability of what? Probability of modulus x bar minus mu less than epsilon is what? Is equal to 1. And what does that mean? Therefore x bar is a consistent estimator of mu, or you can say that the sample mean is a consistent estimator of the population mean. Usually a population mean is denoted by what? Mu. Okay, so that's how we have solved this. And next we will move on to the next problem, that is we have to show that the sample variance is a consistent estimator of the population variance. So here things will be a bit different, and yes, let's see how we will prove that. So again, we know that the expectation of S square, we have studied it as what? N minus 1 divided by n into sigma square. What about the variance of S square? 2 into n minus 1 divided by n square sigma raised to 4. Okay, now what I'm going to do is that we have to show that the expectation of the sample variance or the sample variance is a consistent estimator of population variance. So we have to show that this expectation of S square tends to sigma square and variance of S square tends to 0 when n tends to infinity. Okay, so basically we have to show that expectation of S square tends to sigma square, variance of S square tends to 0 as n tends to infinity. So let's see what we can do for that. So instead of we will write as expectation of S square is equal to, instead of this n minus 1 by n, I'm going to make a small change over here, nothing but 1 minus 1 by n. I hope this is fine with you, multiplied by sigma square. So as n tends to infinity, let me mark this as a becomes what? Equation A becomes expectation of S square is equal to 1 multiplied by, as n tends to infinity, this part will become 0 into sigma square. So expectation of S square tends to sigma square. So first part is okay with us. Now what about this condition? Variance of S square. Now variance of S square is 2 into n minus 1 divided by n square multiplied by sigma raised to 4. So this again I'm going to rearrange it as 2 into 1 by n minus 1 by n square into sigma raised to 4. Okay, so as n tends to infinity, let me mark this as equation B. B becomes what? B becomes variance of S square is equal to 2 into, now this becomes 0, this becomes 0, 0 multiplied by sigma raised to 4, which is equal to 0. Therefore, we can say that expectation of S square tends to sigma square and variance of S square tends to 0 as n tends to infinity. Therefore, we can say that S square is a consistent, S square is a consistent estimator of sigma square. Or we can say that the sample variance, this is the sample variance is the consistent estimator of population variance. Okay. So the next problem is that if t is a consistent estimate of theta, then show that t square is also a consistent estimate of theta square. So we just have to show that limit n tends to infinity, probability of modulus t square minus theta square less than an epsilon, let that be epsilon 1 is equal to 1. This is what you have to show in order to prove that t square is a consistent estimate of theta square. So now let's start with limit n tends to infinity, probability of modulus t minus theta less than epsilon. Okay, now this implies limit n tends to infinity, probability of I'm going to introduce now the minus theta value over here. Sorry, I'm going to introduce instead of this modulus, I'm going to write this as minus epsilon less than t minus theta less than epsilon. Okay, I hope this is fine. How this became the second equation, I hope you all know, which implies limit n tends to infinity, probability of, now this theta, I'm going to add a theta over here. So in all the three terms I'm going to add, so theta minus epsilon less than t, here the theta is gone and you have epsilon plus theta. Okay, now what I'm going to do is I'm going to square each term so that I get probability of theta minus epsilon the whole square less than t square less than epsilon plus theta the whole square. Okay, now this implies limit n tends to infinity, probability of you can expand this as theta square plus epsilon square minus 2 theta epsilon less than t square less than epsilon square plus theta square plus 2 epsilon theta. Fine. Okay, now what I'm going to do is which implies limit n tends to infinity, see, instead of okay, now what I'm going to do is, in the next step, probability of this theta square is taken over here. I'm going to add, or I'm going to subtract theta square from each of these three terms so that I get epsilon square minus 2 theta epsilon less than t square minus theta square less than epsilon square plus 2 epsilon theta. Fine. Now what I'm going to do is I'm going to see, anyways this term is a very small value, so I'm going to write this as limit n tends to infinity probability of uh, minus epsilon square. Okay, I'm going to take this minus part outside, plus 2 theta epsilon less than t square minus theta square less than epsilon square plus 2 epsilon theta. I hope this is fine. Now this is of the form, see, this is of the form minus a less than b less than a. Now what does that mean? How can you rewrite this equation as? Yes, you can write this as modulus b less than a. So applying this over here, what will you get? Probability of, sorry, limit n tends to infinity probability of modulus t square minus theta square less than epsilon square plus 2 theta epsilon. Right, now this I can write this as anyways epsilon is a positive quantity, so this is epsilon plus, or epsilon square is also a positive quantity. Epsilon square plus something positive is again a positive quantity, so I'm going to term this as epsilon 1. Now this implies what? Limit n tends to infinity probability of t square minus theta square less than epsilon 1. Okay, now this is equal to 1. Why? Because we just came from here where this inequality, we already know this inequality as 1. Right, now considering, I'm going to make this as equation 1. Considering equation 1, considering equation 1, this will become 1. That is, limit as n tends to infinity, or as n becomes large, probability of t square minus theta square modulus t square minus theta square will be less than epsilon 1, and that will be equal to, or that will tend to 1, or will be equal to 1. Hence, if we get an equation like this, what does this mean? This means that what I said in the beginning, we just have to prove that this thing is equal to 1. So it is, we can say that t square, therefore t square is a consistent, t square is a consistent estimate of theta, of the population parameter theta. So those are the 3 problems that we have did. Now the next problems we will do it in another class. Thank you.